Hi all. In the last lecture, we have seen the Dirichlet inverses and Mobius inversion formula and a new arithmetical function, Mangold function. After that, we have seen the divisor sum formula for this Mangold function. Now, in this lecture, we will discuss two sections, 2.9 and 2.10. 2.9 is 2.9 deals with multiplicative functions. That is a new definition. New definition is there, and uh, after all, we will see an important subgroup of the group of all arithmetical functions with f of 1 not equal to 0. So that is the importance of this section. Before we start with the definition of a multiplicative function, an arithmetic function f is called multiplicative if f is not identically 0 and if f of mn equal to f of m into f of n whenever m comma n is equal to 1. That is GCD of m comma n is equal to 1. So the one thing you should remember is the definition of arithmetical function, we are dealing with only non-zero arithmetical functions. Okay. So zero function definitely satisfies this condition f of mn is equal to f of m into f of n whenever m comma n is equal to 1. If we consider f is equal to zero function, then LHS and RHS will be zero. Zero function satisfies this equation, even though we are not considering that zero function as not as a multiplicative function, because in the definition itself it says that f should be a non-zero function. Another definition is completely multiplicative function. Completely multiplicative function, we start with the multiplicative function and having the condition f of m n is equal to f of m into f of n for every value of m comma n, okay, without any restriction for m comma n. Say GCD of m n is equal to 1. So we are not considering not considering all those restrictions. Then, if we choose a multiplicative function f with this condition f of m n is equal to f of m into f of n, then we can say that that is a completely multiplicative function. An immediate example is f alpha of n, that is equal to n raised to alpha, is completely multiplicative, because we know that f alpha of mn is equal to mn raised to alpha, that can be written as m raised to alpha times n raised to alpha. If alpha is equal to 0, then this f alpha coincides with u. One important remark is every completely multiplicative function is multiplicative. So that is evident from the definition itself. So we have another examples. For multiplicative functions, we can consider mu of n. Mu of n is multiplicative, phi of n is multiplicative. We have already proved that phi of n satisfies the condition phi of mn is equal to phi of m into phi of n. If m comma n, GCD m comma n is equal to 1. This mu of n is also multiplicative. So one exercise is you need to prove this mu of the statement mu of n is multiplicative. Of course, these functions mu and phi are not completely multiplicative, because you can easily verify with one or two particular value, typical value for this m and n, and verify that formula. So you will see this phi and mu do not satisfy the condition for multiplicative function. Now, u of n and I of n. U of n is identity function. U of n is nothing but u of n is equal to 1 for everyone. These two functions are completely multiplicative, along with the function we have discussed in the previous slide, f alpha. So you may verify. We have another important arithmetic function is there, that is Mangold function. So you can verify Mangold function is multiplicative or not. That is an exercise. I left it to students. So we have some remarks on there. The first one is the ordinary product fg of m is equal to f of m into g of m. If you define the point-wise multiplication and point-wise division, with proper condition g of n not equal to 0, we can get these fg and f by g are all completely multiplicative and multiplicative as well. If then in this remark, you can see the first one is the definition of pointwise multiplication and uh, pointwise division, and in the second and third remark you can get if f and g are multiplicative, so their product and quotient are also multiplicative. Similarly, if both are completely multiplicative, then the product and quotient will be completely multiplicative. So these are the three remarks. Now we have theorem. That is a very simple theorem. One line we can write a one line proof for this. If f is multiplicative, then f of n is f of 1 equal to 1. So we start with the multiplicative function. So one thing you remember is f is always a non-zero function. Okay? So there exists at least one n with f of n not equal to 0. So we start with a multiplicative function f, then f of n can be written as f of n into 1, that is f of n into f of 1, or f of 1 into f of n, since gcd of n comma 1 is 1. Then now we choose such point. Choose a point n such that f of n not equal to 0. Such point exists because this f is multiplicative. That means f is non-zero function. So at least one such n exists. So if we cancel both sides, cancel this f of n from the both side, we will get f of 1 is equal to 1. That's very simple. So this function, this is nothing but a necessary condition. This is not sufficient. At least for the time being, it is not sufficient. Okay, okay, next theorem is in this section we have simple theorems. So next section is next theorem is if for a given f with f of 1 equal to 1, then f is multiplicative if and only if f of p1 raised to a1 into p2 raised to a2 etc. pr raised to ar is equal to f of p1 raised to a1 into f of p2 raised to a2 into etc. f of pr raised to ar for all primes pi and all integers pi greater than or equal to 1. Okay? So this can be considered as a characterization of multiplicative function. So the next statement will give the characterization of completely multiplicative function, that is nothing but f of p raised to a is equal to f of p whole raised to a for all primes p and all integers greater than or equal to 1. So I didn't include the proof of this theorem in this slide, so you need to do separately, or you must try to write the proof of this theorem uh, in your words. If you encounter any doubts or lack of clarity, please contact me. I will give you the suggestions. Now we move on to section 2.10. In this section, we will discuss multiplicative functions and Dirichlet multiplication. We start with the theorem: if f and g are multiplicative, so their Dirichlet product is also multiplicative. So we start with f and g. F and g are multiplicative function. Then we define h is equal to f star g. We should remember the formula of star g. F star g of n is equal to sigma d divides n f of d g of n by d. Clear? So and we take two arbitrary integers m and n, both are relatively prime. So we need to prove that h of mn is equal to h of m into h of n. So we start with h of mn. H of mn is actually the formula is sigma d divides n, d divides mn, d divides this h of mn is nothing but f star g. So this is f star g of mn. So how do you write f star g of mn? Sigma d divides mn f of d g of uh, mn by d. Okay, so d divides mn. That means d is a divisor of mn. Then we need to evaluate f of d and g of mn by d. But any divisor of mn can be decomposed into uh, the product of two divisors of m and n, because if d is a divisor of mn where mn and n are relative prime, then d can be written as d is equal to ab, where a divides m and d divides n. So sigma d divides mn f of d g of mn by d can be written as sigma a divides m B divides n, f of AB, G of Mn by AB. This is nothing but the replacement of that D by AB. That is equal to sigma A divides M, B divides N, f of A, f of B, since this f is multiplicative. Similarly, you can write G of M by A, G of N by B. Uh, since M and N are relatively prime, then this A and B are relatively prime. A by M and N by B are relatively prime. All those nice properties there. So we can separate this f of AB and G of M N by AB. So this is same as sigma A divides M f of A, G of M by A, sigma B divides N f of B, G of N by B. This is nothing but the term by term multiplication of these two sums. So that is equal to h of m into h of n. This completes the proof. Next, you have an exercise. Prove or disprove the digital product of two completely multiplicative functions is completely multiplicative. Next, we move on to a theorem. If both g and f star g are multiplicative, then f is also multiplicative. Okay? So for the proof, we start with an f which is not a multiplicative and deduce that f star g is also not multiplicative. That means we are using, we need to prove that g and f star g are multiplicative, then f is multiplicative. So we assume the converse, f is not multiplicative. So we will prove that this f star g is not multiplicative along with g is multiplicative. Okay? So our assumption is g is multiplicative, f is not multiplicative. We need to prove that f star g is not multiplicative. Clear? So if we put h is equal to f star g, our assumption is f is not multiplicative. F is not multiplicative means there exist two positive relatively prime integers m and n such that f of mn not equal to f of m into f of n. Means f is not multiplicative means there exists at least one such pair. We choose a pair m and n for which the product mn is as small as possible. If there exists at least one pair, we will choose the smallest such pair. Smallest in the sense that mn is very small. Okay, mn is the smallest one. If mn is equal to 1, then clearly m equal to 1 and n is equal to 1. So our assumption is f of mn not equal to f of m into f of n, that is f of 1 not equal to f of 1 into f of n. This implies f of 1 not equal to 1. Clear? So f of 1 not equal to 1 means f is from this you can write f of 1 not equal to 1. If f of 1 not equal to 1, then the following equation, using the following equation, we can prove that h is not multiplicative. Our assumption is f star g is multiplicative, but we will prove that f star g is not multiplicative. That means h is not multiplicative. So we start with h of 1. H of 1 is equal to f of 1 into g of 1. That is equal to f of 1 because g is multiplicative. Our assumption is g is multiplicative, f is not multiplicative. So f of 1 into g of 1 is equal to f of 1. That is not equal to 1 from the previous sentence. This shows that h is not multiplicative. That is f star g is not multiplicative. So what you have proved is if mn is equal to 1, that is the least possibility. If mn is equal to 1, then the conditions f is not multiplicative, g is multiplicative together imply that f star g is not multiplicative. Okay, so this proves the theorem if mn is equal to 1. Now we assume mn greater than 1. Okay, then we have f of ab is equal to f of a into f of b for all positive integers a and b with the gcd of a comma b is equal to 1 and ab is less than mn. This is because of the choice of this mn. Mn is chosen in such a way that mn is the least product for which f of mn is not equal to f of m into f of n. So for any pair a comma b whose product is less than mn satisfies this condition. F of ab is equal to f of a into f of b. Now we start with h of mn. H of mn is equal to sigma a divides m, b divides n, ab less than mn, f of ab into g of mn by ab plus f of mn into g of n. This is nothing but the extraction. If you consider sigma a divides m, b divides m, f of ab, g of mn by ab. If we extract the one term a is corresponding to a equal to m and b is equal to n, we will get the last term of the right side. So this is nothing but an extraction. Then sigma a divides m, b divides n, ab less than mn, f of a, g of b, g of m by a, g of n by b, because we have assumed that g is multiplicative, and for any pair ab which is less than for any pair a comma b, if ab since ab is less than mn, we have f of ab equal to f of a into f of b. So from the induction or the above hypothesis, we can split this f, and from the assumption from the theorem itself, we can get g is multiplicative. So we can distribute the first sum as in this manner, that is equal to sigma a divides m, b divides n, product is less than mn, f of a, f of b, g of m by a, g of n by b plus f of mn. That is equal to, this is as same as the previous the techniques in the previous theorem. Sigma a divides m, f of a, g of m by n, m by a, sigma b divides n, f of b, g of n by b, minus f of m into f of n plus f of m. That is because if you consider this product of these sums, you will get extra term f of m into f of n. That is not included in the previous statement. So we minus that f of m into f of n from this product. So this this constitute f of m n, sorry, h of m into h of n minus f of m, f of n plus f of m. So we have assumed that this minus f of m, f of n plus f of mn not equal to 0, because we have chosen mn in such a way that mn is the pair for which this equation f of mn equal to f of m into f of n does not hold. So this contradiction completes the proof. So as a consequence of the previous theorem, we can prove that if G is multiplicative, then G inverse is multiplicative. Because if G is multiplicative, then G inverse, that is nothing but I, that is multiplicative. So G and G star G inverse is multiplicative, then using the previous theorem, we can say that G inverse is multiplicative. So that is a relation between the directional multiplication and multiplicative inverse of arithmetic function. So, so this is an important connection between multiplicative functions and dirichlet multiplication. So this completes the section 10. So please go through it and try to answer the question given in the exercise. And if you have any doubts, please contact me, or I will schedule a Google Meet for the doubt clarification. Thank you.